Welcome, everyone. Today, we are going to explore the orchestrator's blueprint, which maps out the incredible evolution of tool use in LLM agents. We're moving far beyond the early stages where agents were limited to isolated, single-point API calls. From there, we evolved into intermediate sequential multi-tool sequencing. Now, we have finally arrived at the era of long-horizon orchestration, where agents dynamically generate execution graphs, retrieve memories, and run parallel operations while autonomously handling errors and refining their output. So, how exactly are we escaping the limitations of linear reasoning? If we look at the architectural comparison, the past linear era forced agents to execute tools sequentially. If one tool failed, the entire system halted and failed. Today, in the orchestration era, we use parallel execution and directed acyclic graphs, or DAGs. Instead of binary selection, we navigate combinatorial dependencies, meaning if a task fails, the agent can dynamically reroute, adapt, and roll back. This shift to topological planning is essential to overcome what we call autoregressive myopia. Traditional step-by-step generation falls into the autoregressive trap, suffering from context exhaustion and early-step error accumulation. By treating execution as a state space search rather than simple text completion, models can combinatorially navigate tens of thousands of APIs. This enables a powerful think-simulate-act paradigm, allowing internal simulators to evaluate consequences before taking real actions. To sustain these complex, long-horizon executions, we use a cognitive division of labor. Think of this as a dual-system cognitive architecture. System 1 acts as the executor, handling the fast, localized processing of high-volume tool outputs. System 2 is the planner, using slower, logical reasoning to prevent the agent from drifting off goal. Both systems interact with a memory vault that persists across sessions, compressing completed tasks into progress briefs. This centralized scheduling separates workflows into planner, caller, and summarizer roles, helping specialized models easily outperform monolithic ones. Now, how do we train these agents? Let's look at the spectrum of agent tuning. For the lowest computational cost, we use training-free methods to dynamically unlock API activation. As we scale up data dependency, we use trajectory synthesis for high-scale formatting and long-tail coverage. Next is supervised fine-tuning, or SFT, which aligns syntax and format constraints. Finally, for the highest capability, we use reinforcement learning. While it has the highest cost, RL unlocks strategic exploration and the ability for the agent to self-correct. Generating the synthetic data needed for these advanced agents requires an evolution engine. This engine works in three parts. First, a synthesis mechanism for structural graph generation. Second, a tri-stage execution validation checking format, execution, and semantics using virtual API simulators. Third, coverage expansion to capture long-tail error patterns. The critical metric here is no longer just the quantity of data, but the systematic coverage of complex interactions and failure recoveries. Let's zoom in on why reinforcement learning is so important for self-correction. SFT simply trains models to myopically imitate syntax. When an execution error happens, the system halts without any recovery mechanism. RL changes the game by offering turn-level credit, granular rewards that isolate exactly which step caused a failure. By balancing global strategy with local exploitation to mitigate entropy spikes, RL empowers the agent to adaptively roll back and explore new solutions. But this orchestration power comes with risks, because concurrent execution breaks traditional trust boundaries. Parallelizing read operations is fine, but concurrent write operations risk catastrophic data collisions and state inconsistencies. To solve this, agents need database-style transaction semantics that allow for safe rollbacks. We also rely on pre-execution constraints to intercept high-risk operations via self-verification before any changes are committed. Another massive risk in long-horizon chains is the contamination cascade. Continuous parameter bindings can cause the agent to drift away from its safety baselines. If a malicious payload is introduced, it can illegally propagate downstream, turning the agent into a confused deputy and masking the root cause of a system failure. To stop this, we implement circuit breakers, using tree search to predict downstream risks and sever contaminated chains before execution. To keep these systems efficient, we have to decouple logic from execution. Traditional synchronous systems suffer from dead time where the agent is just blocked, waiting for an API to return. Orchestration uses asynchronous decoupling and speculative execution. The system predicts subsequent actions before the current tool even returns a result. Combined with semantic caching, we can retrieve historically verified API results and completely bypass redundant processing. What happens when an agent enters an open environment and doesn't have the right tools? It synthesizes them. First, the agent perceives its boundary, identifying missing tools or ambiguous intents, and triggering clarification. Then, it autonomously expands its toolset, using code generation to create new tools or aggregate basic APIs into composite skills. Finally, it commits these successful new tools into a persistent experience memory, transitioning from a passive tool user to an active tool creator. Because these capabilities are so advanced, our evaluation methods have to evolve to measure systemic intelligence, rather than isolated functions. We now test topological complexity through nonlinear DAG executions. We evaluate temporal scale by pushing horizons past 50 steps to test context saturation. We shift to dynamic environments with interactive simulators, and demand state persistence, meaning the agent must actively self-critique, diagnose errors, and propose fixes. Ultimately, engineering constraints dictate how these executions look in the real world. Web and GUI environments require tight perception action loops to manage visual noise. Software engineering demands expensive verification loops like patching and compiling. Enterprise scenarios are governed by strict transactional topologies and auditability. Mobile environments demand conservative recovery and explicit user confirmation. Across the board, success has shifted from just sounding right to robust, testable functional verification. To tie it all together, we use the unified master architecture. Incoming topologies, whether they are serial, branch, parallel, nested, or retry structures, feed into a centralized execution engine. This engine continuously loops through planning, acting, observing, and revising. At the same time, it embeds functional correctness directly into the graph through execution gates, constantly checking verity, safety policies, and latency costs. This brings us to the true frontier of industrial orchestration. To move from usable prototypes to dependable, auditable systems, we need explicit infrastructure-level guarantees. This means building evolvable tool governance that adapts without complete retraining. It means defining verifiability boundaries with mathematically provable audit trails. And it requires transferable error recovery libraries alongside budget-aware routing that dynamically allocates resources based on uncertainty. Thank you for joining me on this deep dive into the blueprint of modern AI agents.